The second to the last thermodynamic process is the isentropic process. We can visualize this by using a piston cylinder arrangement that is completely covered with a perfect insulation. This insulation does not allow heat to get in or out of the thermodynamic system. So the only way by which gas inside the piston can expand is by having a high initial temperature. The expansion will then cause the volume to increase based on Boyle's law, and the temperature of the gas to drop based on Charles' law. Notice that since no heat is transferred during the process, then it should be reflected in the TS diagram by a vertical line going from point 1 at the top to point 2 at the bottom. This is the shape of the TS diagram since there should be no area below the TS diagram. An area below the TS diagram just means that either heat was transferred during this process, which is not possible for an adiabatic process, or there are inherent irreversibilities present in the process, which is also not possible for a reversible process such as the isentropic process. As always, we can use the equation of state of ideal gases as one of the ways by which we can express the relationship among pressure, volume, and temperature. Now, the exact solution to find the values of P, V, and T at different points in the process involves the alternative form of the equation of state of ideal gases. Finally, the approximate solution involves the following formulas. Notice that in the exact solution, we do not use the specific heat ratio of the gas, but in the approximate solution, we use a single value for K. The reason behind this is that in the exact solution, we consider the specific heat of the gas to vary with temperature. But in the approximate solution, we consider the specific heat to remain constant. That's why we can afford to use a single value for K in the approximate solution. I will now derive the formula for the approximate solution in the next slide. Let us first derive this part of the formula. For us to derive this, we are going to use the fact that during an isentropic process, the product of the pressure and the kth power of the volume remains constant. We can extend this formula further by using the values of the initial pressure and volume in our formula instead. Therefore, we can separate all the pressure on one side of the equation and all the volume on the other side of the equation. Finally, by raising both sides of the equation to 1 over k, we will be able to derive one side of the formula above. Now let's derive this side of the formula. For us to derive this, we are going to use the alternative form of the equation of state of ideal gases, which also corresponds to the exact solution for finding the relationship among P, V, and T. Now we can write the formula in this way. We isolate all temperature factors in the left side of the equation, while the pressure and volume factors are at the right side of the equation. But isn't it that the ratio P2 over P1 is just equal to V1 over V2 raised to k? So we can replace P2 over P1 by V1 over V2 raised to k in the right side of the equation. In addition, by using the laws on exponents, the remaining factor V2 over V1 can be written as V1 over V2 raised to negative 1. By further using the laws on exponents, we can simply write the right side of the equation in this way, since we are multiplying two powers having the same base. Finally, by raising both sides of the equation to 1 over k minus 1, we will be able to derive the other side of the formula for the approximate relationship of pressure, volume, and temperature during an isentropic process. Now, the approximate and exact solutions for the change in internal energy and the change in enthalpy are just the same with those in the isobaric and isometric processes. On the other hand, the heat transferred and the change in entropy in an isentropic process are just both equal to zero. Now for the non-flow work, this can be computed using the non-flow energy equation or by using the area under the PV curve. In the derivation using the non-flow energy equation, remember that we can just zero out Q since no heat is transferred anyway in an isentropic process. So we will be left with the non-flow work being equal to the negative of the change in internal energy. Remember that in the exact solution for the non-flow work, we use the values of the specific internal energy of the gas based on its ideal gas property table. On the other hand, the approximate solution for finding the non-flow work can be found from finding the area bounded by the PV curve. One of the simplifying assumptions in this formula is based or one of the simplifying assumptions in which this formula is based on is that the specific heat ratio stays constant. Therefore, I will now be deriving this formula in the next slide of this presentation. To evaluate this integral, we must first express the pressure P in terms of volume. But we know that for isentropic processes, the product of the pressure and the kth power of the volume is just equal to an arbitrary constant. Therefore, we can use this equation to express P in terms of V. This will allow us to arrive at this form of the integral. Again, we can simply take out the arbitrary constant C from the integral. By using the simple power formula, we'll now be able to get the integral of this function. Then we can apply the limits of integration in the integral that we obtain, thereby allowing us to arrive at this form of the equation. Now to simplify this, remember that the arbitrary constant is just equal to PV raised to K. Since this product just remains constant anyway, then we can express this equation as the product of the initial pressure and the kth power of the initial volume. Or we can express this as the final pressure times the kth power of the final volume. Therefore, by distributing the constant factor C to the two terms in the numerator, we will arrive at this form of the equation. Finally, by using laws of exponents, we can further simplify the formula using this alternative form.